All right, let's get right into it. Weather. It's something we all talk about every single day. But have you ever really stopped to think about the massive planetary forces at play that create a simple sunny day or a crazy thunderstorm? I mean, what's the fundamental reason we even have weather?
Right? We get it all. Sunshine, rain, snow, you name it. But the why behind it all is this incredible planetary story. It's a drama playing out constantly right above our heads. And you know what? We're about to figure out the plot.
So that's exactly what we're going to do. Think of us as detectives. We're going to piece together the fundamental clues that create every single cloudy day and every perfect sunny afternoon. So, are you ready for the first clue? Okay, clue number 1. It all begins about 93 million miles away with our star, the Sun. The Sun is the engine. It is the single biggest, most important driver of everything we call weather. Without it, our atmosphere would just be, well, static and lifeless.
And here is the absolute key to this whole thing. The sun's energy is massive, yeah, but it doesn't hit every part of our planet the same way. This imbalance, this uneven heating, is basically the spark that lights the fuse for all weather to happen.
This shows it perfectly. Think of the sun's energy like a flashlight beam. At the equator, that beam hits the Earth dead on, super focused and intense. That's a lot of heat. But at the poles, that same beam hits at an angle, so the energy gets spread out over a much larger area. It's more of a glancing blow. And that simple difference, hot equator, cold poles, is the first major piece of our puzzle.
So you've got these hot spots and cold spots on a planet that's wrapped in this big blanket of air. What happens? Well, nature hates an imbalance. It wants to even things out. And that effort kicks off this massive planet-wide movement of air. It's like a giant conveyor belt.
This is just basic physics, but it has enormous consequences for our planet. It's so simple. Hot air is light, it's floaty, it wants to go up. Cold air, it's heavy, it's dense, and it wants to sink right down to the ground.
And you can see that whole cycle right here. The air at the superhot equator warms up, gets light, and rises high into the atmosphere. From there, it starts to move toward the colder poles. As it travels, it cools off, gets heavy again, and sinks back down. And that sinking air then gets pulled back towards the equator to replace the air that's rising. It's just this constant, churning global loop.
And just like that, we have wind. Seriously, every breeze you feel, every gust of wind is just a tiny part of this gigantic global system of rising and sinking air, all powered by the sun. Without this movement, the air would just sit there.
Okay, so we've got our engine and we've got air moving all over the place. But, moving air by itself doesn't create a thunderstorm or a blizzard. For that, we need to add 2 more crucial ingredients to our weather recipe: pressure differences and, of course, water.
This breaks it down beautifully. Wherever that warm air is rising, it creates a zone of low pressure. You can think of it as there being less weight of air pushing down on you. And that rising, cooling air is the perfect setup for clouds and storms. On the flip side, where that cool, heavy air is sinking, you get a high-pressure zone. And that usually gives us those nice, clear, calm days.
So low pressure creates the conditions for a storm, but to actually get rain or snow, we need the star ingredient, water. And the crazy thing is, even on the clearest day, the air all around us is packed with invisible water vapor.
And here's the journey it takes. The sun's energy evaporates water from oceans and lakes, turning it into that invisible gas. That vapor then gets a ride upwards on those rising air currents. But as it gets higher, it gets colder, and the air just can't hold it as a gas anymore. So it condenses back into teeny tiny liquid droplets or ice crystals, and voila, you've got a cloud. When those droplets get big and heavy enough, they fall.
So let's recap. We have our engine, the sun. We have the reaction, which is moving air. And we have the ingredients, pressure and water. But there is one last massive clue that shapes how all this plays out. And that's the simple fact that our planet spins. Yeah, have you ever really thought about that? Why do hurricanes have that beautiful, iconic swirl? Why doesn't the wind just blow in a perfectly straight line from high pressure to low pressure? Well, the answer adds a really cool twist to our whole story.
It's called the Coriolis effect. Now, don't let the fancy name scare you. Think about it like this. The Earth is spinning really fast at the equator, but it's barely moving at the poles. So as air tries to travel in a straight line from, say, the equator up to the North Pole, the ground is literally spinning out from underneath it. This causes its path to curve to the side. And that curve is what gives huge storms their spin and organizes winds into the global patterns we see.
And there we go. We've collected all our clues.
the sun, the movement of air, the pressure, the water, and finally, the Earth's spin. So now it's time to put it all together and finally solve the mystery of why we have weather.
So here's the solution. Weather isn't just one thing. It's the constant interaction of these 4 key drivers. They fit together like giant puzzle pieces. You've got the sun's uneven energy creating temperature differences. That causes air to move. The water cycle throws moisture into that moving air, and the Earth's spin choreographs the entire dance. If you take away any one of those pieces, the whole picture just falls apart.
And because all these pieces are always moving, always interacting, always in flux, so is our weather. It's this dynamic, sometimes chaotic, and honestly beautiful system that is never exactly the same from one moment to the next.
So now we know the recipe for weather here on Earth. But that leaves us with one last, really fascinating question to chew on. Imagine a planet that had a sun, and an atmosphere, and water, but it just stood perfectly still. It didn't spin at all. What kind of weather do you think you'd have then? Something to think about.